Good morning, everyone. Today I will be presenting a paper on learning Agile robotic locomotion skills by imitating animals, published at RSS 2020. The work comes from a collaboration between Google Research and UC Berkeley, with the lead authors being Xieping Pan. This paper tackles one of the long-standing challenges in robotics, getting a legged robot to move the way animals do, and it does so using a surprisingly elegant imitation learning approach. Here's how I will structure the presentation. I'll start with the motivation and problem statement to set the context. Then I will walk through each of the three stages of their framework: motion retargeting, motion imitation with reinforcement learning, and domain adaptation. After that, I will cover the experimental results and finally wrap up with the discussion and conclusion. So why is the problem hard and why does it matter? If you look at animals, dogs, cheetahs, even insects, they navigate complex environments with incredible agility and fluidity. Robots, on the other hand, still struggle to match that level of performance. The traditional approach is to handcraft controllers for each behavior, but this is time-consuming, requires deep expertise, and the resulting motions often look stiff and unnatural. Reinforcement learning offers an alternative, but designing reward functions that produce the exact behaviors you want is itself a laborious process. And on top of that, policies trained in simulation tend to fail when you actually put them on a real robot. So the question this paper asks is, instead of designing everything from scratch, can we just show the robot what to do by letting it imitate real animals? Let me formalize that idea. The goal of this work is to take a reference motion clip, for example, motion capture data recorded from a real dog, and automatically synthesize a control policy that allows the physical robot to reproduce that skill in the real world. On the input side, you provide a motion clip. On the output side, you get a deployable controller. There are three important constraints. First, no skill-specific reward engineering. The same reward structure should work for all motions. Second, the method must bridge the simulation to reality gap, sim to real gap, because training on a real robot from scratch is too expensive. And the third, the real-world adaptation should be sample efficient, meaning that it should not require thousands of trials on the physical hardware. The framework they propose has three stages, shown here in the overview figure. Stage 1 is motion retargeting. Since the dog and the robot have different body proportions, the mocap data cannot be used directly, so they first adapt the motion to fit the robot's morphology. Stage 2 is motion imitation. They use reinforcement learning in simulation to train a policy that reproduces the retargeted motion. Domain randomization is applied here to prepare the policy for real-world variation. Stage 3 is domain adaptation. Once the policy is trained in simulation, they transfer it to the real robot using a sample-efficient latent space adaptation technique that only requires around 50 real-world trials. I will now go through each of these stages in detail. The first stage is motion retargeting, and the challenge here is a morphology mismatch. A dog's body proportions are quite different from those of the Lycodo robot, the name of the paper. Their solution is inverse kinematics. They define a set of key points on both the dog and the robot, specifically the positions of the forefeet and the hips. As you can see in the figure here, each key point on the dog has a corresponding key point in the robot. At each frame of the motion clip, the dog key points give you target 3D positions. You then solve an optimization problem to find robot joint poses that track those target positions as close as possible. There is also a regularization term in the objective that keeps the robot pose close to a natural default pose. This prevents the IK arm from finding physically unreasonable solution just to hit the target. The second stage is motion imitation, framed as a reinforcement learning problem. The policy maximizes the expected discounted return in the standard RL sense. Let me highlight the key design choices. The state includes the robot's poses over the last 3 time steps and the last 3 actions. Importantly, the robot position, that is, the global 3D position of the robot's body is excluded. This is a practical choice. You do not need to estimate global position when deploying on a real robot. The goal is to look ahead over 4 future reference poses, spanning roughly 1 second into the future. This gives the policy anticipatory information about where the motion is headed. The action specifies the PD controller, target angles for each joint, and the low-pass filter is applied before sending command to the hardware, which helps produce smoother motions. Training using PBO with approximately 200 million simulation samples per skill, and the policy is required at 30 Hz. The reward function as weight is a weighted sum of 5 terms, each measuring how closely the robot tracks a different aspect of the reference motion. The pose reward penalizes differences in joint angles. The velocity reward penalizes differences in joint angular velocities. The end effector reward penalizes differences in foot positions relative to the body, and the 2 root rewards track the global position and the velocity of the robot's torso. All 5 terms have the same exponential form, so they smoothly decay toward 0 as the tracking error increases. The key insight I want to emphasize here is that this reward function is completely general. You do not write a new reward for each skill. You just provide a different reference motion, and the same reward structure automatically encourages the robot to learn that new behavior. This is what makes the framework scalable to a more diverse set of skills. Now let's talk about the third and most technically novel stage, domain adaptation. The fundamental problem is the sim to real gap. Even if your policy works perfectly in simulation, the real world has different friction, different motor dynamics, sensor noise, latency, all the things your simulator does not perfectly model. Their approach has 2 parts. First, during simulation training, they applied domain randomization by varying six dynamics parameters: mass, inertia, motion strength, the mortar friction, latency, and lateral friction. These variations train the policy to handle a range of conditions rather than just one fixed environment. But domain randomization alone is not enough for dynamic scale. So the second part is a latent space adaptation method. The dynamics parameters are encoded into a low-dimensional latent variables z by a learned encoder. The policy is conditioned on z when transferring to the real world. They search for the best z on the physical robot using only about 50 trials. You can see the network architecture here. The encoder maps dynamics parameters to a Gaussian distribution over Z. The policy then takes the state, the goal, and the Z as inputs. There's one more important ingredient: the information bottleneck. The concern is this: if the policy has unconstrained access to the dynamics parameters through Z, it can learn to overfit very precisely to each simulated environment. That sounds good in simulation, but it means the policy becomes brittle. Small differences between simulation and reality cause it to fail. Their solution is to add an information bottleneck that constrains the mutual information between the dynamics parameters and the latent encoding. In practice, this is implemented as a KL divergence penalty between the encoder distribution and the standard Gaussian prior, weighted by a coefficient beta. The effect of beta is intuitive. A large beta forces the policy to ignore most of the dynamics information, making it more robust but less adaptable. A small beta lets the policy use more information, making it more adaptive but more brittle. Through experiment, they find that beta equal to 10 to the power of -4 strikes the best balance. I will show the ablation results in a moment. Once the policy is trained, how do you actually find the right Z for the real robot? You do not have access to the true dynamics parameters, so you cannot just run the encoder. Instead, they frame it as a search problem. They want to find the Z star that maximizes the return when executing on the physical system. They use advantage weighted regression, or AWR, to do this search directly in the latent space. Starting from a Gaussian prior, at each iteration they sample a Z, run one episode on the real robot, record the return, and then update the search distribution to put more weight on Z values that gave higher returns. This is remarkably sample efficient. The table on the right shows the hyperparameters only 10 gradient steps per iteration, and the whole process converges in roughly 50 real-world trials, which take between 5 and 10 seconds each. So in practice, adaptation takes only a few minutes of real robot interaction. Let me now describe the experimental setup. The robot is the light cargo quadruped, which has 18 degrees of freedom, 3 actuated joints per leg, plus 6 under-actuated root degrees of freedom. Simulation is done by bullet. Training uses PPO with around 200 a million samples. The motion dataset is a mix of real dog mocap from a public dataset and artist-generated animations. In total, they train policies for 10 different skills. The table here shows the domain randomization ranges. Notice that the testing range is deliberately larger than the training range. This is to evaluate out of distribution generalization. They want to see how well the policies handle dynamics they have never seen during training. Here are two of the skills learned by the system. Each strip shows from top to bottom the reference motion, the simulated robot, and the real light cargo robot. The top strip is the dog pace gait, where legs on the same side of the body move together. This is typically used at slower speed. The bottom strip is the hop turn, which is particularly impressive. The robot performs a 90-degree turn while leaving the ground, a highly dynamic behavior that would be extremely difficult to encode manually. Let me see whether I can find YouTube of this. Okay. Right. Of course, like to provide a paper presentation on this YouTube, and I'll provide the link later. Where were we? Okay, the learned skills, right? So here are 4 more learned skills, and the top that is a backward trot, which they obtain simply by playing the mocap clip in reverse. Interestingly, the policy reaches a higher speed than the forward trot, 1.2 meters per second versus 1.08. The top right is a side step, which requires lateral foot placement, which is quite different from standard forward gait. Bottom left as a turn motion learned from an artist animation. Even though artist animations are not physically correct, the policy still manage to produce a reasonable approximation on the real robot. Bottom right is a running man, which is the most challenging skill. It requires the robot to travel backwards while mimicking a forward walking motion. The policy partially succeeds, but tend to shuffle rather than fully lift its feet. Let's see whether they do provide the 4 skills in the official YouTube. I believe so. Okay. They do provide. There's a dog trot, and then there's backward pace, and this is the side step. So there's a lateral foot placement, and this is turn. So this is from the animation. This hop turn is the most difficult one. So you can see there's some failure, but wouldn't say it's failure, it's just partially succeed for this particular task. Anyway, yeah. So the bar chart summarizes real-world performance across all 10 skills and trace methods: no randomization, the robust non-adaptive baseline, and their full adaptive methods both before and after the real-world AWR adaptation. The pattern is clear. For dynamic skill like dog pace and dog spin, the no randomization policies essentially fail in the real world. The world. You can see their bars are very short. The robust policy does better, but still falls short. The adaptive policy after real-world tuning achieve by far the highest performance. For simpler quasi-static skills like in-place steps and side steps, the robust policy is actually sufficient. Adaptation does not help much because the dynamics are not as challenging to transfer. So this chart provides a more intuitive view of the same phenomena. It measured how long the robot stays on its feet before falling. The adaptive policies consistently maintain balance for longer, and in many cases, they reach the maximum episode length without falling at all, which is why several bars extend to the right limit of the chart. The non-adaptive policies fall much earlier on dynamic skills. This directly illustrate why adaptation matters. A policy that is merely robust to simulated variation is still not robust enough for real-world deployment on agile behavior. And these curves evaluate policy performance across 100 out of distribution OOD simulated environment. Environments with dynamics parameters sampled from a wider range than was used during training. Read the horizon axis as the fraction of environment and the vertical axis as the return threshold. A curve further to the right means the policy achieves higher return in a larger fraction of environment. The adaptive policies consistently outperform the robust baseline. For dog pace specifically, the adaptive policy exceeds a return of 0.6 in 50% of environment, compared to only 38% for the robust policy. This shows that the learned latent dynamics encoding genuinely helps generalize beyond the training distribution. This ablation experiment studies the effect of the information bottleneck coefficient beta. The dotted line shows performance before adaptation, and the solid line shows performance after. You can observe the trade-off clearly. Larger beta values start with higher pre-adaptation performance. These policies are most robust but show less improvement after adaptation because the policy does not rely much on Z to begin with. Smaller beta values shows the opposite. Lower pre-adaptation performance but a larger gain after adaptation because the policy is more sensitive to Z and can therefore benefit more from finding a good Z on the real robot. The no IB, the condition, no information bottleneck, so there's no IB. So there's no information bottleneck at all. Performs worse overall. Without the constraint, the encoder overfeeds to simulation dynamics and the policy is too brittle to transfer well. Beta equals to 10 to the negative 4 gives the best balance and is widely used in all experiments. So here is the full numerical summary for a selection of skills. A few numbers worth calling out. Dog pace goes from 0.128 with no randomization to 0.35 with a robust policy, and the way up to 0.8 with the adaptive methods after real-world tuning. This is more than a six-fold improvement over the baseline. Dog spin shows a similar story, 0.098 versus 0.75. As I mentioned, in-place stabs and side stab are the exception. The robust policy already achieves near maximum performance because these skills do not require highly precise dynamics matching. The overall message here is that for any skills that is dynamically challenging, the adaptive approach is very essential. The authors are honest about several limitations. First, very dynamic behaviors like the large jumps or fast running gaits could not be reproduced on real hardware. The actuators and mechanical structure of the light cargo robot simply do not support those motion yet. And second is the learned controllers are still not as stable as the best handcrafted controllers from the manufacturer. There's room to improve robustness. Third, each skill is trained as a completely separate policy. There is no multi-skill policy that can switch between behaviors. The most exciting future direction in my view is learning from videos. If you can extract motion priors from YouTube videos of animals, you suddenly have access to an enormous amount of behavioral data without any need for mocap equipment. To summarize, this paper makes three main contributions. The first one is a unified three-stage system retargeting imitation, adaptation that works for a wide variety of skills without skill-specific reward design. Second, an information bottleneck technique that provides a principled way to trade off between robustness and to simulation, variation, and adaptability to new real-world dynamics. And third, an empirical demonstration that this approach produces genuinely agile behaviors on real quadrupeds, including skills that exceed the performance of the manufacturer's own controller. I think the broader lesson here is that reference motion data is an extremely powerful source of prior knowledge for robot learning. Rather than designing reward functions from scratch, we can leverage the wealth of natural motion that animals already demonstrate. Thank you for listening, and if you have any question, just post it on the discussion forum on the course website. Thank you. And then you can see the project page and videos on GitHub and YouTube also. Thank you for your time today.